So today and tomorrow I want to give some introduction to this theory of regularity structures, which is essentially what allows us to give a meaning to these very singular kind of stochastic PDEs that we saw in the first lecture. It's not the only theory that does so. So I think you've had a sort of short lecture by Pierre about paracontrolled distributions, which is a sort of alternative theory. Both have sort of advantages and disadvantages. So, okay, so it kind of depends on the problem, which one's more convenient. In some sense, the difference is analogous to the difference between measuring the regularity of a function by looking at its Fourier transform, or measuring the regularity of a function by looking at its Taylor series. Okay, so in some sense, regularity structures are more like Taylor series, paracontrolled distributions are more like Fourier transforms. So to start with, today I want to give some actual math, and so the first thing I want to discuss is how do we, so since the solutions to these stochastic PDEs are sort of irregular, so they might be distribution valued, or for example, you might have the derivative showing up on the right-hand side and the derivative is distribution valued. So the first question we should ask is, how do you measure the regularity of a distribution? So what does it mean for a distribution to be sort of worse behaved than another distribution? And the standard way of doing this is to basically test it against sort of bump functions that are rescaled like a delta function, right? So you take, so phi, here you should think of the function phi as being some kind of bump function, like this. It's just an arbitrary, compactly supported smooth function. And then you rescale it so that it sort of scales like a delta function, right? So you kind of translate it, so you center it around some point x, and then you rescale it so that horizontally the support has size about lambda, where you think of lambda as being small, and the height here is going to be sort of lambda to the minus the dimension of your space, so that the integral doesn't change, right? So you sort of rescale it like you would do an approximate delta function. And then you test your distribution against such a function, right, against such a test function. Now, if the distribution were actually given by a continuous function, then as lambda goes to 0, this would just converge to the value of that function at x, right, because it's an approximate delta function, or maybe times the integral of phi. Now, since this is a distribution, in general, this may not converge as lambda goes to 0. It may actually diverge. And so one way of measuring the regularity of a distribution is to basically just check how fast it diverges as lambda goes to 0. And then you say that a distribution is in C alpha if when you test it against such a test function, you get something which is bounded by lambda to the alpha. And you have to, you have to do the right kind of uniformity over class of test function, but you basically take test functions that have, say, support bounded, the diameter of the support bounded by 1, and all of their first 10 derivatives bounded by 1. And then that gives you the correct definition as long as alpha is bigger than -10 or something, right? And if you want to go below that, then you impose that the first 20 derivatives are bounded by 1. And the value of 10 or 20 doesn't matter, right? So the norms you get are all equivalent. And so you want this to be uniform over test functions such as just described, uniform over lambdas in 0, 1, and locally uniform in x. Okay, so that's a definition of C alpha. And it actually coincides with the usual definition of C alpha, right? So the Holder space is C alpha that you all know. This definition, if alpha is positive, right? So if alpha is positive, that definition doesn't quite work because, well, this would typically just converge. Even if this guy is a smooth function, this would just converge to the value of the function at x. And so it's not going to go to 0, right? So it's never going to satisfy a bound like this with positive alpha. But actually, it's going to go to 0 if you take a function here that integrates to 0. Right? And so if you take test functions that integrate to 0 against polynomials of sufficiently high degree, then you can actually use a definition like that also for positive alpha. And then it coincides with the usual definition of the Hilbert spaces, at least when alpha is not an integer. For integer values, there's a bit of subtlety. Okay, right, so that's what I just mentioned here. And yeah, for integer values, you get what's called the Zygmund spaces. So somehow the function x log x is in C1 with that definition, whereas of course in the usual definition, it's not. Okay, now in our case, since we're interested in these PDEs, so the example of PDEs that I showed you last time, well, for example, that KPZ equation. So remember that KPZ equation, this was the stochastic PDE given by sort of like a heat equation. Then there was this nonlinearity, which is problematic, and then there's space-time white noise. And so now if we want to measure regularity in space-time, okay, so this is a function of x and t, then, well, here you would take test functions that are functions of space-time. But because of the parabolic scaling, right, you see here that space and time naturally scale differently. So there's one derivative in time which balances two derivatives in space. So the natural thing to do is when you do this in the time coordinate, instead of dividing by lambda, you divide by lambda square. So that's what we mean by parabolic scaling, right? So the parabolic scaling is the one where in time you divide by lambda square. And that has then the property that if you apply this heat operator, you have a lambda square coming out, whether you take the t derivative or the second derivative in x. So somehow both of them behave in the same way. Right, so that's the natural way of doing this. And then this n here should be the space dimension plus 2 because of the lambda square dividing the time, right? So that's what makes the integral again remain constant. Okay, so now that gives us a good way of measuring sort of the size of a distribution or the regularity of a distribution. And then now, remember the problem that we have, if we look at an equation like this KPZ equation, is that we want to take, right, so here we want to take the square of the derivative and the function is not differentiable. And so this is sort of identically infinite in some sense. So you want to still find some natural definition of that square, which also makes a physical sense. And so you can ask yourself, when can you actually multiply distributions? Right? So turns out that if you take distributions that are random, in particular if they are random and Gaussian, so Gaussian in the sense that when you test it against any test function, you get a Gaussian random variable. And if you test it against finitely many test functions, you get jointly Gaussian random variables. Actually, the first property already implies the second one. So if you take such random distributions that are furthermore stationary, then it turns out you can actually kind of multiply them in situations where you shouldn't be able to. And so what I mean is, well, so take the following example. So if psi is centered Gaussian and the covariance sort of behaves like this, right? And of course, this doesn't quite have a meaning because you can't evaluate psi or zeta here at a point x. But what you should really mean by this, right, is that if you take zeta of phi, now this is perfectly well defined, and zeta of psi, then this should be equal to integral phi of x, psi of y, and some kernel of x minus y, dx dy, and that kernel k should be bounded by x minus y to the minus 2 alpha. Okay, so that's what I mean when I write this. And so you take a random distribution like that. It's not very difficult by some sort of Kolmogorov type argument to show that the regularity that such a distribution would have is, well, it would be in C minus alpha, but actually C minus alpha minus delta. Okay, so you lose a little bit, so that's the usual thing, like in Brownian motion, is not quite C a half, but it's a half minus delta for every delta. So, okay, so, and it's no better than that, okay, in the same way as Brownian motion is not actually C a half, right? And so such a random distribution is not in C minus alpha, but it's in C minus alpha minus delta for every delta. Okay, so now we have a random distribution. It's statistically stationary because we assume that the covariance is some function of x minus y only. And it has negative regularity, so it's a genuine distribution. And so you can ask yourself, is it possible to square such a thing? Okay. And it turns out that, well, you know, so in general, you can't. Right? So that's what I mentioned already last time, is that if you ask yourself, so from an analytical point of view, you know, for which alphas and betas is the product a continuous map on C alpha times C beta, then the answer is that, well, it is the case if and only if alpha plus beta is strictly positive. Okay, and that's an if and only if. So in that sense, well, I know if you have a guy which has negative regularity, then you can't take the square, because the square, well, you know, you would have C alpha times C alpha, and alpha plus alpha would be negative. Now, on the other hand, one thing you can always do is take convolutions, right? So take convolutions is not a problem. You can take any, you know, so for example, there's a problem with the behavior at infinity. Okay, so you have to make sure things are sort of integrable at infinity. But for example, if you take a compactly supported kernel, K, even if K is sort of very badly behaved, so K can even be a distribution, but typically the kind of kernels that we would be interested in are things like the heat kernel or stuff like that. And then it would be a kernel that has some singularity at the origin, and it's sort of a, you know, a well-behaved singularity. But okay, I mean, it's singular, it diverges at the origin. Then in general, you cannot test a distribution against such a kernel, okay, because it's not a test function, because it might diverge. But you can always convolve it. Okay, so convolving a distribution with any kernel, as long as the kernel actually itself defines a distribution, that's well defined. And if the kernel, so this is a sort of famous result, so that's usually called Chowder's theorem, so that if you're in dimension n, and the kernel has a singularity which is of order beta minus n, right? So in the sense that, you know, not, so K is bounded by x to the beta minus n for x small, but also, you know, like the derivative of K is bounded by x to the beta minus n minus 1 and so on. So it really sort of behaves like that without any crazy oscillations. So if you have a kernel like that, then the convolution with the kernel is always well defined for any distribution. And furthermore, you gain some regularity. Okay, so this is very important. If you have a kernel which scales in a way better than a delta function, right? The delta function, you should sort of think of it as being x to the minus dimension. Okay, it's not quite true, but it's almost true. So beta equals 0 corresponds to this being a delta function. And of course, if you convolve by a delta function, that's the identity. And so you gain nothing. And so here, if beta is positive, this is a kernel that behaves a bit better, but it's still divergent at the origin. And then you actually gain precisely the amount of regularity by how many powers of x the kernel is better than a delta function. Okay. And so in the case of the heat kernel with the parabolic scaling, this is 2. Okay, so it's always the case that it's 2, because the heat kernel, well, basically it's, you know, it's bounded by t to the minus dimension over 2, space dimension over 2. But then the actual dimension of space-time, remember n in the case of the parabolic scaling, is really space dimension plus 2. And then powers of t sort of count double. So t to the minus dimension over 2 is really t to the half to the power minus dimension. Okay, so in some sense, this whole power would be minus the space dimension, whereas n would be space dimension plus 2, and therefore beta would be 2. Okay, so in the case of the heat kernel, beta is equal to 2 with parabolic scaling. And so that tells you that if you take any distribution and you convolve with the heat kernel, it increases regularity by 2. Okay, so that's the important thing to take away from that discussion. And now what I mentioned is that, well, if we have this, say, Gaussian random distributions that are stationary and sort of well behaved, well, then we can actually kind of multiply them in situations where, from the analytical point of view, the product is ill-posed or, you know, totally undefined. And the reason why that's the case is that if you, so again, I take one of these centered Gaussian random fields like before. So say I convolve it with some modifier, right? So the rho epsilon here, again, you should think of rho epsilon as being some kind of approximate delta function at size epsilon. Okay, so that's your rho epsilon. So this is going to be an approximation of zeta. And so now, instead of, if I want to define the square, for example, instead of just squaring it, I could look at what's called the Wick square. Okay, so this little diamond sign here, it's basically just a shorthand for saying that instead of taking the square, you actually stick your function into the second Hermite polynomial. Okay, the second Hermite polynomial is x squared minus 1, and you replace all the ones by the variance of your process. Okay, so this is the second Hermite polynomial. And of course, here in the case of the square, the second Hermite polynomial is just about subtracting the expectation. Okay, so all you do is you square it, but then it gets very big, and so you recenter it by subtracting the expectation. Okay. And then it's all for simple calculation that if you look at the covariance of that square, that Wick square, what you get is actually just the covariance of the guy itself squared. Maybe with, I think I made a mistake. I think there's a 3 in front or something like that. Okay, but that's not very important. So the point is that it's proportional to just the variance of zeta epsilon itself squared. And now, well, so if the zeta has a variance that sort of behaves like x to x minus y to the minus 2 alpha, that means that that guy behaves like x minus y to the minus 4 alpha. Right? Well, modified, you know, with the epsilon, but now I can send epsilon to 0, and it's going to converge to something like this. And the important fact here is that as long as 4 alpha is less than the ambient dimension, than the dimension of the sort of ambient space, this is still locally integrable, right? And so in particular, it's a well-defined distribution. And then one can kind of check that in that case, actually, this field here has a limit as epsilon goes to 0. Okay? So this guy doesn't have a limit as epsilon goes to 0, but this guy does have a limit as epsilon goes to 0. Okay, because it's the expectation of zeta epsilon square, that's actually typically going to blow up like, well, basically like epsilon to the minus 2 alpha. Right? So this guy would blow up, but if you subtract that diverging mean, what you get converges to a perfectly nice random distribution. Okay. And what you see is that, well, from this, since the singularity of that new random distribution is sort of twice as strong as that of the old one, well, you would guess at least, and you would be correct, that if you try to measure the regularity of that random distribution, you'll find out that it basically lives in C minus 2 alpha, or C minus 2 alpha minus delta for every positive delta. Okay. So, and you can do that also, you know, you can do the same thing where you multiply somehow two different right? It doesn't just work for the square. I can just multiply two different Gaussian, stationary Gaussian random fields in this way, provided that the sum of the regularities is bigger than minus dimension over 2. Okay? So that's important. And the regularity of what I obtain in this way is basically going to have the sum of the regularities of the two guys that I multiply. Okay, but since regularities are negative, sum of the regularities is lower than somehow the minimum of the two. Okay, so usually when you multiply two Hölder functions, the regularity of what you get is the minimum of the two regularities. So here, if you multiply two Hölder distributions in this sense, well, you don't have any other good way of multiplying them, then the regularity you would get is actually the sum of the two regularities. Okay, so that's an important thing to keep in mind. And so now the question is, so this is all nice, but of course it doesn't seem terribly useful as far as giving a meaning to our SPD is concerned, because, well, our SPD, it's a nonlinear SPD. The solutions are not going to be Gaussian. There's not going to be any explicit formula for the solutions or anything. And so, it's not clear, there's no guarantee that any sort of definition like that actually still works. Right? This is a very Gaussian kind of calculation. But still, so we can ask ourselves, well, if we postulate, for example, so we have some random distribution zeta, and we postulate that the square of zeta is that Wick square, okay, that we define in this way as epsilon goes to 0. And that limit, by the way, does not depend on the choice of modifier. Okay, and so it's kind of intrinsically well defined. Well, so if we postulate just that we're able to multiply zeta with itself, then what other things are we able to multiply? Right, so you would think that, well, if I postulate that the product of zeta with itself is that Wick square, well, then if I have a random distribution which somehow looks like zeta, so for example, a multiple of zeta, or zeta plus a smooth function, or maybe zeta times a smooth function, right? Well, then I still know how to multiply those, right? So the question is, how far can you take that kind of line of reasoning? Yeah. And so then the main idea of the whole theory is the following. So what you want to do is you want to build a theory that somehow smells very much like Taylor expansions, but you replace the Taylor monomials, so like x minus x naught to the k, you replace them by, arbitrary distributions or functions, right? That might be random even. And then, but then still, so then you're going to kind of try to describe your solution to your SPDs, for example, locally by some kind of Taylor expansion, but now the coefficients are not the coefficients in front of the Taylor monomials, but the coefficients in front of these things that are going to replace the Taylor monomials. And then the philosophy is that, well, if we know how to multiply, for example, any two of these replacements for Taylor monomial, well, then it sounds reasonable that we should be able to multiply any two distributions that have somehow a kind of Taylor expansion with respect to these guys at sufficiently high order, right? So that's somehow where this is going, right? So you assume, so you're given, say, a bunch of distributions, you assume that you know how to multiply those, right? So maybe there's a natural way of doing it, or maybe you just pull the product out of a hat. So, of course, what you would like is to have a natural way of doing it, like we had here. But you just postulate the product of these guys within some reason. So you have to give yourself some kind of analytical constraint. So, and then you ask yourself, well, what does this imply? So what does it tell us about things that locally look like these distributions? Okay, so can we then multiply those? Okay, so then in order to do that, of course, first we have to actually understand the classical Taylor expansions, right? So of course, you know, all of you have seen Taylor expansions in your undergraduate studies. But okay, so I want to just, this is as much for fixing notations as anything else. But still, maybe it might give a slightly different perspective from the one you might be used to, okay? So of course, when you want to do Taylor expansions, there's a natural algebraic structure there, which is the space of polynomials, right? So I'm going to write R of X here. So that's just the usual ring of polynomials in one indeterminate, or maybe as many indeterminates as you have dimensions in your space. But let me just stick to one. It doesn't make any difference if there's more than one. I'm going to write this indeterminate as a purple X. And so this space of polynomials, well, it has a natural grading, right? So there's the constants that have degree 0. There's the linear guys that have degree 1. There's the quadratic guys have degree 2, and so on, right? So that's you have this graded space of polynomials in this purple X. And now so what I want to do, okay, so now the usual perspective is to say, well, I'm given a function, say I have a function from R to R, and then what does it mean for the function to be C gamma? Well, it means that it has a Taylor expansion up to order gamma, okay? And so in other words, it means that, well, locally you can, you have a value for your function, you have a value for the derivative and so on, and up to integer part of gamma. And then if you subtract the corresponding Taylor expansion, the remainder is of order sort of x minus y to the power gamma. But now I want to make a slightly different shift in perspective and say, instead of viewing a C gamma function as a real valued function, okay, I want to view a C gamma function as a function that actually takes values in that space of polynomials, okay? And you should think of it in this way, right? So at every point now, instead of just having the value of the function, I also attach, the derivative, second derivative divided by 2 and so on, up to, derivative of order integer part of gamma, okay? And then, well, there are two natural operations here, right? So on the one hand, I have a natural evaluation map. I have a collection of evaluation maps, right? So if I take this purple X, which is just an abstract symbol here, well, I want to view it as, the argument of a Taylor monomial. But Taylor monomials are always monomials in like x minus x naught, or if you want y minus x. Okay, so you always fix a base point around which you perform your Taylor expansion, and then you have a polynomial in dot minus that base point, right? And so that means that you have a collection of natural evaluation maps that depends on that base point, okay? And that basically turn the purple X into the linear function that intersects, the origin at the base point, okay? So into the function, if you want, z minus x, okay? So that, I view it as a linear map, right? So pi x of the purple X to the n is a function, and it's the function, z minus x to the n. So if I apply, right, so if I describe a C gamma function in this way, if I apply this pi x to f of x, right, so if I look at pi x of f of x, then this is actually the Taylor expansion viewed as a function, right? The Taylor expansion at x viewed as a function of z, if you want, okay? And the other important property of Taylor polynomials, well, polynomials, if you want, in general, is that if I have 2 points, 2 base points, x and y, now, of course, if I have a polynomial in z minus x, I can always rewrite it as a polynomial in z minus y, right? Because I can always write, well, z minus x to the k, I can write it as z minus y plus y minus x to the k, and then I can just do the binomial expansion, right? And so I have a map gamma xy, which performs that re-expansion, right? So I can view this gamma xy as a map from t to t. And what it does is it takes the coefficients, right? So it makes sure it's just the map which guarantees that pi x gamma xy is equal to pi y. Right? So it basically takes coefficients in an expansion around y and turns them into the coefficients for an expansion around x. Okay, it just re-expands a polynomial in z minus y into a polynomial in z minus x. Okay, I can view that as a collection of linear maps from t to t, and well, here's the explicit expression, right? So this is just a re-expansion. And so, okay, so this satisfies this coherence property here, and it also satisfies this property here, right? So that's two very natural properties. So it's just, on the one hand, this just says what I just explained, and this says, well, if you have a, if you have coefficients of a Taylor expansion based at a point z, and you re-expand it to view it as a polynomial in dot minus y, and then you re-expand that to view it as a polynomial in dot minus x, well, then of course it's the same as just taking the original guy and re-expanding it around x in the first place, right? Because in some sense, as a function, I do nothing, and I don't change the function. Right? I just change the way I'm describing the function. But now with these definitions, with these two objects, so that pi x and this gamma xy, I actually have a very nice formulation of the Holder norm. Okay, so the thing is, the usual Holder norms, it's always slightly messy, right? Because you say, oh, if alpha is between 0 and 1, then of course you just take f of x minus f of y divided by x minus y to the alpha. But then if alpha is between 1 and 2, then you have to look at f of x minus f of y minus, y minus x, f prime of x or something like that, and then divide that by x minus y to the power alpha. And so you have to somehow, depending on which two integers you sit in between, you have to somehow subtract the Taylor expansion up to that value in order to define your Holder space. So my claim is that the correct definition of the Holder space is C gamma is the following. So you give yourself not a real valued function, but you give yourself a function with values in these polynomials. So if you want, you give yourself a candidate Taylor expansion at every point. Okay. At this stage, there's no guarantee that f prime of x is the derivative of f of x. Okay, so you just give yourself a function f prime, a function f second, and so on, and you mash them together into one function capital F in this way. Okay, so at this stage, I don't impose anything about f prime actually being the derivative of f, or f second being the second derivative of f. Okay, so they are just independent functions. Okay? And then I have a natural Holder norm on these kind of jets, if you want, which is given in the following way, right? So I want to do, it's some kind of Holder norm, and so I want to compare f of x with f of y, but f of x is something like a Taylor expansion around a candidate Taylor expansion around the point x. F of y is like a candidate Taylor expansion around the point y. Of course, if you want to compare them, well, one of them gives you the coefficients of a polynomial in dot minus x. The other one gives you coefficients of a polynomial in dot minus y. And so you can't just compare these coefficients. That doesn't make any sense, right? I want to first turn one of them, re-expand it around the other point so that both of them are interpreted as coefficients of a polynomial in dot minus either x or y, right? And so what I do here is I hit this guy here with this gamma xy. So that takes coefficients of a monomial in dot minus y and turns them into the coefficients of the corresponding polynomial in dot minus x. Okay, and then I can compare that. And so now I have two polynomials. And so I just compare coefficients. I look at the coefficient in front of the monomial of degree k. So if you want the coefficient in front of purple x to the k. Okay, so these are polynomials in purple x. I look at the kth coefficient, and then I impose that that kth coefficient is of size x minus y to the gamma minus k. Okay. So in particular, the 0th coefficient would be x minus y to the gamma. And if you unpack this definition, what you find is that, well, if you take k equals 0, it precisely states that your candidate Taylor expansion is a Taylor expansion up to order gamma for little f. And therefore, in particular, f prime actually has to be the derivative of f by definition of what the derivative is. And then if you look at the higher values of k, like k equal 1, for example, basically it says similar things for f prime. It essentially says that, if you look at the coefficient here, what's left ends up being a Taylor expansion for f prime. But then, of course, for f prime, it's only a Taylor expansion up to order gamma minus 1. And so the natural thing to do here is to divide by gamma minus 1. Right? So in general, if you look at the kth coefficient, the natural thing to do is to divide by gamma minus k, x minus y to the power gamma minus k. And the claim is that this is just the usual, this is totally equivalent to the usual gamma Holder norm. Okay, but it's just a neat way of reformulating it. Okay. But the nice thing here is that I never, so the difference is I never need to compute the derivative. Okay, so taking a derivative of a function is a slightly weird operation, right? It's a sort of very unstable kind of operation. So here, I sort of shift the point of view the other way around. I just give myself a candidate. Okay, so I just give myself these function ff prime and so on. And then I have a norm, which is really some sort of supremum type norm. Right? There's no derivatives involved in this norm. And then if that supremum is finite, well, then I know for a fact that this guy actually had to be the derivative of f, that f had to be differentiable and this guy had to be the derivative of f. Okay. So that's sort of a very nice property of this way of looking at it. But the other nice property is that this way of looking at it generalizes. Okay, so now what we can do is we can basically keep all of this structure, but we forget about the fact that this guy, right? We just, don't impose that this pi x guy gives me, the function dot minus x to the k. And we don't impose that this is actually the ring of polynomials. So that's what we do now. Okay, so that generalization, so that's the definition of a regularity structure. So 40 minutes in, I'm sort of at the first definition. I think yeah, okay, I might be going too slowly here. So the definition here is, well, basically just take deconstruction of the previous slide and just remove all references to polynomials, but keep everything else. Okay, so that's somehow the definition. And so you say, okay, so you start with a graded space. So that's the analog of this ring of polynomials here. But the grading doesn't need to be by integer. Okay, so in general, my grading needs to be sort of discrete and bounded below, but it doesn't need to be an integer grading. So you could have negative degree, for example. Okay, but it needs to be bounded below, so there needs to be a smallest degree, but the smallest degree doesn't need to be 0. Okay, it could be -1 or something. It could be -0.5. Okay, it doesn't have to be integer either. And then you also have a group G, actually a Lie group that acts on T. So that's the analog here. This group would be the group of translations, right? So this gamma, there's actually a group action here, which is the group of translations, right? So Rn, well, R here. So R with addition as its group structure acts on this space by just mapping X to X plus, your element of R. And this is a group action. And these gammas are of the form you know, some guy in that group action for some number, and the number being x minus y. Okay, so we keep that structure. So we have a group that acts on T, and we assume that it acts in the same way as sort of, you know, translating a Taylor monomial acts, in the sense that if I take a monomial of a certain degree, right? So here being in T alpha, that's the analog of being a monomial of degree alpha, right? A homogeneous polynomial. So if I take a homogeneous polynomial of degree alpha and I translate it, right? So if I have x to the k, and now I look at x minus h to the k, and then I re-expand it, then what property do I have? Well, the highest order term doesn't change, right? If I expand x minus h to the k, I still get x to the k, and then minus blah, blah, blah. So the highest order term doesn't change. And then I have lower order terms appearing, but I don't have any higher order terms appearing. Okay, and so I want to keep that structure. And so this is what this says, right? So it just says, if I take a guy which is homogeneous of degree alpha, I apply any group element to it, then it gives me the same guy back plus stuff of strictly lower degree. Okay, so that's just the analog of that property. And then, so that's the definition of a regularity structure. So that's if you want the algebraic data in this business. And then there's some analytic data, right? So in the previous case, we had these maps pi x and gamma xy that turned a sort of abstract polynomial in this purple x variable into a concrete function, right? Into an actual function on R. And so here, well, we do the same. So we just, you know, don't impose anything. So we just say a model. So it's a collection of linear maps, pi x as before. Now they don't need to be functions. They're allowed to be distributions. Okay. And I also have a collection of gamma xy's. And well, they should satisfy exactly the same identities as before. So in the sense that pi x composed with gamma xy should be pi y, and gamma xy composed with gamma yz should be gamma xz. So exactly the same sort of coherence property as before. And I also want some sort of analytical bound. And the analytical bound says that, well, you know, this degree here should have an analytic meaning, right? So in the sense that a monomial of degree alpha, the property of a monomial of degree alpha is that it vanishes around a point at order alpha. And so here these are distributions, so I can't, so what do I mean by vanish at order alpha? And alpha could be negative. So then it sort of diverge at order alpha. So here the natural thing to do is what I did, you know, on the very first slide. So test against these approximate delta function and then ask yourself how big the answer is, right? So you take a monomial of degree alpha. So you take, so degree tau is equal to alpha really just means tau is in T alpha. Okay, so these are synonymous. So you take a guy which is homogeneous of degree alpha, you apply pi x, so that if you want gives you the concrete monomial. And then you test it with a test function that's centered around the same point x. Right, so if you think of the actual polynomials, for example, for degree 2, you would have a parabola that sort of touches the origin at x. And now I test this with an approximate delta function that itself centered around the same point x. And then, of course, here, if you do that, you can just rescale things and you use the scale invariance of the parabola, you find out that what you get is proportional to lambda square. So you can pick up, and if you take a cubic here, it's going to be proportional to lambda cube, etc. And so you pick out the degree of the monomial by just testing against the test function and see what power of lambda comes out. Right? And so here we just impose this as an upper bound. And then similarly for this testing, so there's a similar kind of property, right? So in the case of polynomials, if you expand, right, like x plus h to the k, what do you get? You get a sum of some binomial coefficients, and then you have things like x to the l and h to the k minus l, right? And so this here is sort of the generalized version of the fact that, like, if I act, right, so I take a monomial of degree alpha, so you think of the alpha as being like this k here, and then I act with x, gamma xy, think of it as being translation by x minus y, so this h here would be x minus y. And then what you get is a sum of terms that are of degree beta less than alpha, right? And so as you see here, L has to be less than K. So you also get a sum of terms of degree less than K. And the size of the term of degree beta. So here, what I mean by this is you just take the component in T beta and you look at the norm of that component. Okay, so it's not a Hölder norm here. It's just the size of the component in T beta. And so you want this component to be of order x minus y to the alpha minus beta. Okay, and so that's exactly the analog of this. Okay, so now I have kept, in some sense, all the properties of Taylor polynomials, except for the fact that they are polynomials. Okay, so I never imposed anything about these things being polynomials. And now I can define the definition of the Hölder spaces now works, right? So I can define a C gamma function, which now I call D gamma, as simply a map from RD into T, and exactly as before, right? So the definition is just that f of x minus gamma xy f of y should be bounded by x minus y to the gamma minus alpha, right? And so here is the component in T alpha should be bounded by x minus y to the gamma minus alpha. Okay, so that's exactly the same definition as before. But now, you know, so you should think of this as being, as give yourself some sort of, you know, candidate Taylor expansion at every point x. And then you have a notion of regularity on these, right, which is given by that. So now question number 0 is, you know, does this make any sense in the sense that, you know, if I take, so this here is a weird kind of object, right? So they're kind of coefficients at every point. I give myself a bunch of coefficients in something that is a bit like a Taylor expansion, but instead of Taylor monomials, I have these pi x guys, which could be distributions. And okay, I don't give myself an actual real valued functional distribution, right? So previously, the actual real valued function was easy to recover, right? Because it's actually just the first coefficient here. So now, in this definition, there's no first coefficient. I don't even impose that there's a guy of degree 0 here, right? So I can't even say the first coefficient is d1 of degree 0. Even if there is a guy of degree 0, I don't impose that it's of dimension 1, right? So I can't do that. But I can ask myself still, these pi x f of x's, they are actual distributions. And I can ask myself, you know, does this guarantee that there exists one actual distribution on my Rn, Rd, say, which has the property that in the neighborhood of every point x, it is very close to this candidate, this pi x f of x. Okay, so does such a distribution exist? And so that's the very sort of natural first question, right? Because otherwise we want to basically now build a whole calculus where we do everything at the level of these coefficients somehow. But then of course, at the end of the day, you want to go back and get an actual distribution. You want to say these things actually describes a unique, you know, actual distribution. And so that's the sort of main theorem in this business, or if you want the fundamental theorem in this business, which says that yes, so as soon as gamma is positive, as soon as you have something of positive regularity, then there exists a unique distribution, which I call RF, which has this property, so that for every point x, if I compare RF with, if you want, the candidate Taylor series at x, okay, then that's two distributions. I subtract these two distributions, and if you are of degree, if you are C gamma, then, you know, by definition of C gamma, you would want to say that the difference between the function and its Taylor approximation is of order gamma, right? And that's what it says here. And so you take, there exists an actual distribution, so that if I compare it to its Taylor approximation, and then I test it against one of these approximate alpha function, I get something which is of order gamma. Okay, and this is again uniform in lambda, sort of uniform in phi, locally uniform in x. And furthermore, this map, this reconstruction map here, has nice continuity properties. Okay, it has some sort of local Lipschitz continuity property, both as a function of f, but also as a function of this model. Okay. Okay, so even if gamma is negative, this is actually still true, but the only thing that goes wrong is the uniqueness. Actually, the existence is still true, and that's kind of useful sometimes. Right. And for gamma equals 0, it's actually just false. I mean, even existence can fail there. Okay. So now I want to explain, so how we're actually going to use this business, right? So we have this neat generalization of Taylor expansions, but now how is this going to be useful? Okay. So the idea now is the following. So you start with your favorite singular SPD, say KPZ, since that's the example I gave last week. And well, that one, of course, there's the problem that, it's not clear what the solution means because it's too irregular, blah, blah, blah. The reason why it's not clear what being a solution means is because the noise that drives it is very singular, right? So you can do the same thing as usual. So you mollify your noise, you hit your noise with the mollifier, then everything is smooth. It's clear what you mean by a solution. And so you have a classical solution map here, right? So the C here stands for classical, S stands for solution. So you have a solution map, and what it takes as an input is an initial condition, a smoothened realization of the noise, at least. So at least for that one, I know how to define the classical solution map. And then it also takes as an input, like in this business, we're actually always going to consider a whole class of equations. And then it takes as an input sort of like which element of the class of equation are we considering. For example, in the case of KPZ, we were really looking at the class of equations which were TTH is dx square h plus dxh square plus noise plus constant. Right? Because remember, the theorem was that if you mollify the noise, then you have to somehow send that constant to -infinity in the right way, and then that has a solution, has a limit. Okay, so that was the theorem I mentioned 2 weeks ago. And so here we have a class of equations which is parametrized by this constant here. Okay, and so I have to tell you also which constant I choose here. Okay, so here you have this classical solution map. That's just solving that SPD. The problem is that, so the reason why I draw this arrow in red is that this map is not continuous in any sort of topology in which this guy converges to its limit. Now, so what we do now is we reformulate, so we want to reformulate the whole equation in one of these regularity structures, right? So we want to actually describe the equation as one of these d gamma element, the solution as one of these d gamma kind of functions. And so for this, of course, we need to, find the correct regularity structure, which is sort of large enough to support the operations we need to do that. And what you do is, well, you do this in such a way that the classical solution map factorizes in this way. So what you do is you take your smoothened out noise, and then from the smoothened out noise, you build a model, right? So you build one of these regularity structures, and then, which is not just polynomials, but contains additional stuff. And the additional stuff is going to represent functions or distributions that are built from the noise. Okay, so you have this map here that builds a model from the noise. And then once you have this model, you can, in some sense, write down a fixed point argument in one of these D-gamma spaces that formally looks the same as the fixed point argument that would give you the classical solution map, except that now everything is formulated in terms of these jet kind of things. And then you can solve that. You get an element in D-gamma and you have that reconstruction operator that turns it into an actual distribution. And then you do that construction in such a way that this commutes. Right? So that in some sense, you just factorize this classical solution map in some very complicated way. Now, what's the advantage of doing that, right? It sounds insane. So you have a relatively easily defined classical solution map. You factor it in a crazy complicated way, which I haven't even described in detail. And so what have you gained? What you've gained is that this solution map is going to be continuous in a topology here on the space of models, which does look like the sort of topology in which the noise would converge. Okay? So that one is actually nice and continuous in the good type of topology in which that one is discontinuous. And that reconstruction map is always continuous. And so of course, since a discontinuous map cannot be factored as, you know, a product of continuous maps, something has to be discontinuous here. What's discontinuous is this map here. But that one is explicit. That's what you've gained. Okay. Is that here you have a complicated map, which is given by the solution to a nonlinear PDE, and you factor it into, you know, another map which sort of looks similar but is continuous, and something which is discontinuous but which is explicit. Okay. But now, of course, if you just, now there's the problem of sending epsilon to 0, and we've seen that, for example, for KPZ, if you don't do anything here, if you just send epsilon to 0 and keep the constant fixed, then it's not going to converge. Right? So if I simply send epsilon to 0 here, then this guy is simply not going to converge to anything. And then what it means here, since these maps are continuous, what it means is that if I just take my noise, I lift it into a model up there, and I try to send epsilon to 0, it just doesn't converge. And so the way you go around this, or what happens in this construction, is that the way you build your regularity structure up there, it naturally also comes with a group action. That's a different group. It's not the group G in the definition of the regularity structure. Okay, so it's a different group, which we call the randomization group, which acts on the space of models for your regularity structure. And it turns out that what happens is that you can find, right? And so this is exactly what I explained how randomization works last time. What you do is you lift your noise into a model here, and that doesn't converge. But you find a sequence of elements in that group so that if you lift your smoothened out noise and then hit it with that sequence of elements, then that converges. Okay, and it turns out that you can do that in such a way that it converges to a limit which is, you know, independent of the way you've modified your noise or anything. Okay, so this you have a nice sort of more or less canonical actual limit there. And of course, what you'd think is, well, this is all nice. So then I have a limit here, and therefore, since this is continuous, I get a limit here, I get a limit here. But the problem is that, well, the fact that this commutes now is broken, right? Because halfway through, I've acted with this group, and so I've just completely messed things up. And so what happens now is it turns out that that same group actually also has an adjoint action onto the class of equation that you're considering. Okay, so there's, of course, there's a condition. You need to make sure the class is kind of large enough. But if you choose your class in the right way, this group, that same group that acts on the space of models here, actually acts also on the space of right-hand sides for your class of equation. And that action is such that this, this commutativity is restored. Right? So in the following way, there's like, now you fix an equation here, right? So you fix that element here. You take your smoothened out noise, you lift it, and now you solve that fixed equation here, but for this modified model, right? So you lift the noise, you act with an element of that group, and you plug it into the solution map for that fixed equation. You solve it, and then you go down. And then that's the same as you take that fixed equation and you apply the same group element, the same m epsilon, to that fixed equation. That gives you a new equation that depends on epsilon. And now what you do here is you solve that new equation with psi epsilon as your noise. And then the claim is what you get here is exactly the same as what you get in that way. Okay, so that restores the commutativity, and therefore, since this guy converges, this one converges. Right? And that's the way in which you get the kind of statement that you have here, that if you choose this constant in the right way, this converges, because changing this constant is done by, you know, that action here of that group element. And you choose the group element that makes this guy converge. Okay, so that's somehow the strategy. And so I'm going to finish with this slide. Right, so here is now the plan of what we want to do. And tomorrow I'm going to sort of give you some elements of how you actually implement that plan. Okay, so you give yourself a class of singular SPDs. First thing you need to do is you need to actually build a regularity structure which is in some sense large enough so that you're able to formulate the SPDE as a fixed point problem in one of these D gamma spaces. And you want this canonical lift also, right, which somehow turns a smooth realization of the noise into a model for your regularity structure. Then you need to do that in such a way, right? You need to guarantee that the space D gamma has a good enough, you know, you need the operations that you need to actually formulate your equation, right? So if your equation involves the square of the derivative of the solution, well, you need to be able to take derivatives and squares, right? So there needs to be a kind of a calculus on these D gamma spaces, which is sufficiently rich to allow you to formulate your equation. Okay, and then you need to show that, you know, it gives you a fixed point problem, which is locally a contraction. So you have some sort of pk iteration, so you get unique solutions. And then you need to do that randomization business, right? So you need to figure out what is that group R, which acts on models, and then show that this group is kind of large enough so that it's actually possible to find, right? So find these group elements M epsilon, so that if you smoothen out your noise, look at the model that's built from it, and then act on it with M epsilon, it converges to a limit. And then finally, you need to identify this sort of adjoint action of that group on the space of equations. Okay? And so, of course, you know, each of these steps could be like a 2 hours talk in itself, right? So I'm not going to go into details through all of that. But I'm going to basically just, you know, focus on one example and give you ideas on how the different steps work in that specific example. And hopefully the example is sort of sufficiently representative that, you know, it gives you an idea of how the whole thing works in general. Okay, so I think I stop here for today. Thank you very much for your attention.
Thank you, Martin, for a very enlightening talk. And now, are there any questions?
Excuse me, could you please give me an example of the group acting on the model?
Yeah, so, well, right. So here, in some sense, so these groups are very simple. So in most cases, that group is really just a copy of RD with addition as a group operation, right? In general, they are nilpotent Lie groups, but in most cases, they're actually just a copy of RD. And in some sense, this was actually such an example, right? So here, if you want, you know, you could imagine here that you have a regularity structure where you have two symbols. So you have X of 3 symbols. So let's say 1, X and X square as before. And pi x of x, pi x of 1 would just be 1, and pi x of x would be your zeta, right? Or say zeta epsilon or so. And then, you know, your pi x of x squared would be, say, if you put a zeta epsilon, you take zeta epsilon square. And then the way you would, then your group here would just be, in this case, this group R would just be R with addition. And the way it acts on this model is by just adding a constant here, right? And so here in this example, we see that if we now choose this constant to be minus the expectation of zeta epsilon square, then this guy actually converges to a limit. But if we don't choose it in that way, if we just mollify and take the square, then it doesn't converge to a limit.
I see.
Right?
Thank you very much. Thank you.
That's the sort of example you should have in mind.
I see. Thank you. Thank you.
So I have a question.
Yeah.
I know as good as nothing about the renormalization group in physics, but my vague memory is that often there seems to be the renormalization group is determined by scaling orders of parameters in the theory. So you were saying that you needed to find a appropriate renormalization group to achieve your aims at the end of the talk. Are there scaling dimensions that play a role there?
Yeah. So so if you want the scaling dimension here is really that alpha. Right? So it's actually the degree here that plays the role of the scaling dimension. Right? You've seen already that here, for example, like, you know, a parabola has scaling 2. So that, okay, so the scaling dimensions in physics, sort of the signs are reversed, right? So that's why if you want to look at positive scaling dimension, that really corresponds to negative alphas, right? And so there are the elements here that have negative scaling, and they are the ones that are going to be relevant for that renormalization, right? And like in the physics language, the scaling dimension would just be minus alpha in a way, but for the negative alphas.
Okay. Thanks.
Mm-hmm. Any other questions?
Yeah, maybe a very naive question. And in the model, does it make sense also to kind of consider, so to say, other models which are not built purely out of the noise, but which are built, let's say, out of solutions of other equations which are kind of in some sense close to the equation you want to study? Or does this kind of revert back to the case where you build everything out of the zeta you had?
Well, in some sense, it kind of reverts to that, right? Because, I mean, the solution itself is just built out of the noise. It's just built out of the noise in a somewhat complicated way. Right? So here, I mean, what makes the model nice is that we're going to build it out of the noise in a kind of polynomial way. So the elements of the model are going to be kind of multilinear functionals of the noise. And that's what makes it sort of sufficiently explicit so you can kind of do calculations with it. There's no, like this is a totally general result. It doesn't refer to anything, right? And so you're right that you're not forced to do that. So there could be situations potentially where, you know, where it would make sense to build a model in a different way. Okay, so the kind of situation that I know of is, for example, if you look at things like periodic homogenization also, then there are some results there that can be reformulated in this language, and that sort of make it, we can give a cleaner kind of reformulation in this language. And then in that case, the model would be totally deterministic. So it would just be like periodic functions that scale in a certain way with epsilon. So that, for example, can be a situation also.
Okay, thanks.
Could I ask a question?
Sure.
Yeah. Yeah. So I was wondering, Martin, whether your regularity structures could help proving, say, conformal invariance of statistical mechanical models, like in the work of Smirnov and his group?
I don't think so, because so here the important thing is that in some sense, at least morally, it's kind of perturbative theory in the sense that what you're trying to describe is something which is not scale invariant, but is in some sense close to something which is scale invariant that you understand well, right? So here, this KPZ equation is not scale invariant, but if I drop the nonlinearity and that constant, then I get this stochastic heat equation, and that one is scale invariant. And furthermore, it's super explicit, right? It's a Gaussian process. You can answer pretty much any question about it. Whereas in this whole conformal invariant business, the problem is precisely in order to construct the scale invariant object.
Yeah, but the underlying defining model is not scale invariant either, right? It converges to.
Yeah, but the problem is to understand the convergence to the scale invariant limit. Right. So here you're in a situation where there is a sort of underlying scale invariant object which you understand very well, right? And you leverage the fact that you understand very well the scale invariant object in order to understand other objects that are sort of nearby in some sense. Okay, so I think in that sense the philosophy is really quite different.
Thanks.
Any other questions?
I have a very basic question. It may even does not make sense, but Martin, here I understand that the map SA and R depends on the equation, because the fixed point method depends on the equation in R. But what about the map psi? Does it also depends on the problem that we are dealing with, or since the modification is, means my question is whether this psi is, the map psi is independent of the equation, or it also depends?
Right, so it's, okay. So, so all of this depends on, you fix a class of equations. So in some sense, if you want, that's like fixing an equation, but there's still some free parameters in it. The whole construction depends on the class of equation that you're considering, in the sense that, well, different classes of equations just give you different regularity structures to start with. And so then the whole structure changes. So in that sense, all of these maps depend on the class of equation that you're looking at. Now, this map depends on which element of the class you're considering, right? Since that guy tells you which element of the class you're considering, whereas you're right that that map does not, right? So that one is sort of more universal than that one, in the sense that that guy depends on which element of the class you're considering, and this one does not depend on which element of the class you're considering, right? And that one also, that one does not depend on the element of the class you're considering. Does that sort of answer the question?
Yes. Thank you.
Are there any other questions? I have a question about the, say, starting point of this construction. You use Helder spaces to measure regularity, and can you replace it with other classes of spaces, like Sobolev or Biesov spaces?
Yes, you can. So, okay, so it depends where. So it's very, okay, so there are two places where you use something that looks like Helder spaces, right? So on the one hand, there's in the definition of a model, because these are sort of locally uniform in X, so they're kind of supremum type bounds. And then there is in the definition of these D gamma spaces. This one is the one that looks really like a Hölder kind of norm, right? So this Hölder type norm, you can build analogs of pretty much any functional space that you can consider. Right, so you can take, you know, because you take your favorite Bezoff space, so you can actually write it. So it's often not written in this form, but if you think a little bit about it, you can easily find equivalent norms that are just written really in terms of the coefficients of the Taylor expansion, and you know, and the norm then makes sense in this context. So yes, so you can replace these D gamma spaces that are really like C gamma. You can have Hölder, you can have like Sobolev or Bezoff or something analogs of these spaces for pretty much all the classical functional spaces. And they satisfy, you know, typically the proofs of the, you know, various embedding theorems, they essentially go through. Right.
Thank you.
And sometimes it's useful to use these spaces. I mean, not Hölder spaces. Yeah.
I would like to ask one more thing regarding the same question. So here you change the definition of Hölder spaces to according to the theory. So do you also need to change the definition for Bezoff spaces?
Yeah. So it's the analogous change, right? So it's not like you can, right? So obviously, I mean, the thing is that in this theory, in some sense, these pi x maps, they play the analog of polynomials, right? And they can be very irregular. So of course you don't want to, you know, you don't want to use the usual Bezoff spaces, right? So you want to use a version of Bezoff spaces in which these guys are considered to be super regular, right? But you do it in the same way as the way you sort of define the Hölder spaces here. Right, so you look at the definition of your Bezoff space, you think about how to rewrite that in terms of the Taylor coefficient, and how to make sure, you know, how to write it properly in a way so that, you know, when you compare coefficients at a point and at another point, what is the correct way of doing the comparison also, right? But then it's all about, you know, you take expressions like this, and instead of having a supremum norm, it's a sort of integral type bound or something, right? I mean, it's, you know, the usual way in which you build Sobolev or Bezoff spaces.
That answers it. Thank you very much for very nice all the explanations.
Yeah.
Let us thank Martin again for a beautiful talk, and thanks to all participants. We will meet tomorrow at the same time. Thank you.
Okay. See you tomorrow then.